The following content is created by Dr. Avitech. Your support and donation will help me continue to offer high-quality educational resources for free. To make a donation, send an email to 6drcyril@gmail.com or comment donations below. In this video, we're going to be looking at the Laplace transform of the hyperbolic functions, that is sine at and cosh at. Now, in the previous video, you'll find out that I expressed sine and cosine in terms of an exponential. Now, in this case, for the sake of this, there's also a way to write sine and cosine in terms of exponentials. So we're going to say this guy, sine at, is the half of e to the at minus e to minus at. That is what sine will give to us for the hyperbolic functions. And then cosh at is half of e to the at plus e to minus at. So you see that kind of similar, kind of similar. But there's a way to derive this. Yeah, there is a way. So this is what we have. So what I will do is, let me start with this guy. So let me find this one first. There's going to be a whole lot of work because I can't just find one and from that very one deduce the other. So I have to find both of them. Well, let's get started. So the Laplace transform of sine at, instead we're going to be putting this expression, this guy. So we're going to say sine at. Now this will be integral from 0 to infinity. Now instead of putting the same sign here, I'll just put its representative. So I'm just going to say this is half e to the at minus e to minus at. And then e to negative st dt. It's just better I do it this way. Then the half can come outside. The half is a constant. So I can bring out this half. So this will become half integral from 0 to infinity. Now here I can expand. So this will become e to the at e to the minus st minus e to the minus at e to the minus st dt. Yep, I can do this. I don't want to put a bracket. But at least ideally, it's supposed to be everything here, then dt. So I don't think I should stress about that. So next thing I'm going to be having is, this will become, let me just put it. Okay, so this will become half integral from 0 to infinity. In this case, let me put the negative st first. Or I'm just going to leave it like that so you do not get confused. This will become e to the at minus st. Now what I've just done, I've applied the rule of indices. These two guys have the same base. Since they have the same base, I need to add up the powers. But adding up when there's a minus, it still means there's still going to be a minus. That's why I escaped writing the plus. Then minus e, this will be minus at minus st, and then dt. So that's what we have. Now this is half integral from 0 to infinity. Now I can say, for convenience, I want the minus st to be first. So this will be e to minus st plus at. It's still the same thing because the at is positive. So if it's coming to this side, it has to be positive. And then minus e, so minus at minus st. In this case, there's really no problem. So I'm just going to leave it like that. Or let me just put it, minus st minus at. Nothing is going to be damaged. It's still going to be correct. And then dt. So this is half integral from 0 to infinity. Now what's common here? T is common. So I want to bring out minus t, just like we've been doing ever since. So this will be minus e to the minus t bracket. Minus we cancel minus, t we cancel t, so s is remaining. Plus minus is minus. And then at over t is a. Then we have a minus e Bring out minus s, sorry, minus t. You see that's common. So minus st divided by minus t is s, minus minus is plus, then at over t is a, and then dt. Now at this point, we can now integrate. So this will become half. Now if we are to integrate this, this will be e to negative t bracket s minus a divided by, you're going to differentiate this power. So this will become minus bracket s minus a. Now we have a minus here. Then this is e. I'm going to repeat everything here. Minus t bracket s plus a. Then divided by the derivative of this. That will be minus into s plus a. And then we have our limit from 0 to infinity. All right. That seems like a lot, honestly. That seems like a lot. Okay. Let's continue. So, what I'm going to do is this. Here's what I'm going to be doing. Okay. So this will be 1 over 2. Now pay attention before you call this magic. Remember that whenever you have this, your e to negative t and all of the rest, when you put in your limits, you always get minus 1. Do you remember? Because I don't want to stress myself over it, since we've done it in the past. E to minus t bracket s minus a, when you put in your infinity and 0, everything here will give you minus 1. No need for you to even bother about the s minus a, because it's a constant, so you are concerned with just the minus t. So let me just do this. This will be e to minus infinity minus e to the 0. When you plug in your infinity and 0, then divided by minus s minus a. And this is a minus e to negative infinity minus e to the 0 divided by minus s plus a. Now this will become 1 over 2. Now at this point, this will just be minus 1. Because this is 0. This expression is 0. Then this one is 1. So you have minus 1 divided by minus into s minus a. And then minus again. This is minus 1 divided by minus into s plus a. Now minus will take care of minus here. Minus will take care of minus here. So what will be left to become half of 1 over s minus a minus 1 over s plus a. Now you want to take the LCM there. You want to have a common denominator. So this will become equal to 1 over 2. Now the common denominator will just be their product. S minus a into s plus a will just be their product. Now when you divide s minus a, we cancel s minus a. So what's left is s plus a. So it will times 1. So this will be s plus a. And then minus s plus a will divide s plus a. What's remaining is s minus a. So it will then times 1. So that's s minus a. So this is 1 over 2 into, let's expand. This will be s plus a minus s plus a. Because minus times s is minus s. Minus times minus a is plus a. Divided by, if you look at this denominator, it's a difference of squares. So this will just be s squared minus a squared. Now this is half. S minus s is gone. A plus a is 2a divided by s squared minus a squared. Now 2 will cancel out 2. So what's remaining is a divided by s squared minus a squared. And with this, we have found the Laplace transform of psi at, or should I say sine hat. So this is what we have. So we're going to say this is the Laplace transform of psi at. So this is equal a divided by s squared minus a squared. So that's what we have. Very, very interesting. Okay. Next, let's find the Laplace transform of cosh at. But in this case, I don't really want to do everything from scratch. Of course, the process is actually the same. You can see that they are similar. They're actually similar. The only difference is minus and plus. They're actually similar. So instead, what I'll do is just before there was a shift, just before these two things are going to be different, let me pick up that very location. Now you notice when you come to this very part, this is where everything changes here. This is where everything changes. This is where everything changes. This very place. That's where everything changes. Because everything will be the same. This will be plus, because we're talking about cosh. This will be plus. Everything. So in fact, up to this very point, will still be plus. So that's why I said they're almost similar. They're almost similar. So I don't want to stress myself by going through this again. So instead, what I would do is, I would say that the Laplace transform of cosh at, I'm going to just pick this location. 1 over 2 into s plus a. But instead of writing minus here, I'm going to put plus. S minus a. Then divided by s minus a into plus a. I can actually do this because that is where they became different. So like I said, they're almost similar. Just this location, that was where they became different. So this will become half. Now s plus a will just be s plus a. Then here, this will be s minus a. When these two things multiply, it's a difference of squares. So that's s squared minus a squared. Now this will be half. S plus s is 2s. A minus a is 0. It's gone already. Then divided by s squared minus a squared. Now 2 can cancel out 2 here. So this is s divided by s squared minus a squared. And this will be the Laplace transform of cosh at. There was just no need for me to go and start every single thing from the beginning. That would just make the video very, very long because the process will still be the same. So let's take a look at some examples. Remember to hit the subscribe button, like this video, and share it across to your classmates. So this will be, let's find the Laplace transform of sine t. Now what will be the Laplace transform of sine t? Laplace transform of sine t, what is a here when you compare it? A is what? Sorry, we're looking at hyperbolic functions. Sorry. Let's say 7t. Okay. Now in this case, the value of a here is 7. The value of a here is 7. So this will become 7 over s squared minus 7 squared. So that would be 7 over s squared minus 49. So this is what we have. How about we have number 2? The Laplace transform of Sint. S-I-N-H-T. Now in this case, a is what? A is 1. A is 1. So this will be 1 over s squared minus 1 squared. So that's 1 over s squared minus 1. That's what we have. 3. Let's say we have the Laplace transform of cosh 4t. Now in this case, we're talking about cosh. So the value of a is 4 in this case. Value of a is 4. So this will become s over s squared minus a squared. But a is 4. So this will be 4 squared. So we have s over s squared minus 16. So that's how to apply all of this. And if you remember, this is actually similar to cos and sine. Actually similar to cos and what? Sine. The only difference is our denominator has a plus when you have sine and cos. That's the only difference. And with this, I'm going to call it the end of this section. Let's take a look at another one. Let's multiply by t. What's going to happen if we have a multiple of t? So let's move to the next video. Bye.